Hello everyone. You hopefully have your notes in front of you and you're ready to start talking about residuals and residual plots and influential points. So here we go. First, what is a residual? A residual is a measure of the error. Technically, the way what I want you to write out is it is the difference between an observed value and of the response variable and the value that's predicted by the regression line. The reason we do lines of best fit and the reason we do regression lines is so that we can make a prediction. Now we're going to make a prediction to figure out what could happen at each individual point. But at some of those x values we actually know what happens because we observed that value. So the question is, how far off are we from our predicted from our observed? So that's what a residual shows us. It shows us how far off are we from our observed value with what the least squares regression line is predicting. One of the things about the sum of the residuals, if we were to take all the residuals and add them together, it is always going to be 0. And that's just a characteristic of a line of best fit. A least squares regression line, if done correctly, you should always get 0 when you add up the residuals. You should always remember that the error is the observed minus the expected. We're going to be talking about residuals for the rest of this course, and there's the formula. Residual equals y minus y hat. So you should write that down, make a little note of it. You need to remember what that formula is. Okay, so here's a set of data. We have shoe size and height. So as you can see, as shoe size goes up, the height goes up. And then we're going to find a line of best fit. Y hat equals 1.87x plus 51.36. Now for each shoe size we can plug in the numbers and we can figure out what the predicted height would be. So for 8.5, if I were to plug 8.5 in, I would do 1.87 times 8.5 plus 51.36 and I would get 67.255. And then I would do the same thing for 9. I'd plug in 9 and I get 68.19. And then I do the same thing for 9.5 and I would get 69.125. Now I would like for you to finish that row on your own at some point. It doesn't have to be right now, but it needs to be done before you come into class. And for the ambitious among you, you may figure out a way to do that in list 3 and have your calculator do all the work for you. If you think you can figure out how to do that, I encourage you to try it, and then you can bring it into class and show it to your teammates tomorrow. Now that we figured out, I'm going to assume that you figured out all those predicted values. Finding the residual is easy. It's just the observed minus the predicted. So in this case, the first case, it would be 66 is the observed minus the predicted of 67.255, and we would get negative 1.255. And for the second column, we do 68.5 minus 68.19, and we get 0.31. And we would do it again and again. Once you've calculated all the residuals, the next thing you're going to want to do is to build a residual plot. The residual plot is nothing more than a scatter plot, and it's a scatter plot that shows the x's with the residuals. Those are your pairs. So instead of x comma y, we're doing x comma residual. The residuals don't have to be graphed against the x. They can also be graphed against any other statistics, but generally we graph them against the x. And the reason we do this, the purpose behind doing a residual plot, is to figure out if there is a linear association between the x and the y variables. If there is a linear association, the residual plot will show us that, and if there's not, it will also show us that. If no pattern exists between the points in the residual plot, then the association is linear. So you make a residual plot, and you look and you say, is there a pattern there? If you do not see a pattern, that means it's linear. That means the least squares regression line, there is a linear association between those variables, and the least squares regression line should work for us. If there's a clear pattern, then the association is not linear. It's something else. Maybe it's exponential or quadratic or something like that. So here's an example of a residual plot, and you can see it has no clear pattern, so we would say that one is linear. Here's an example of a different residual plot, and you can see that there is a clear curved pattern, definitely not linear. So on your notes, you should write down both of these examples to give you a good idea of what a linear pattern looks like and what a non-linear pattern looks like. If you need to, press pause, and then we'll move on to the next slide. Okay, so here's another set of data. We're all about data in this chapter. One measure of the success of knee surgery is post-surgical range of motion for the knee joint following a knee dislocation. The question is there a linear relationship between age and range of motion? And we want to sketch a residual plot. So looking at this, you can see there's no pattern in the residual plot, so therefore we can conclude that there is a linear relationship between age and the range of motion. What if we plot the residuals against the y-hats? How does this residual plot compare to the previous one? So remember previously we did the x's, this time we're going to do the y-hats. There's the y-hats. Save you some time this time. How does that compare? Well, let's compare them side by side. Do you notice any difference? I hope not, because they're the same. Residual plots are the same, no matter if you plot them against the x or the y-hat. So they are telling you clearly no pattern means there is a linear association between the two variables. Alright, so if we use a least squares line to predict the values of a response variable, then we can also calculate the standard deviation of those residuals. So we have this big long column of residuals. We can calculate the standard deviation of those residuals using our standard deviation formula. So it's the same formula that we learned a couple of chapters ago, and we would just calculate the residual standard deviation. And the reason we do that is because it will give us the approximate size of a typical or average prediction error. So we'll say on average, how far off are we? And that formula is given to you now. You take your residuals, and the big little sum symbol means after you square them all, you add them all up, you divide by n minus 2, and then you take the square root. And that is the standard deviation of the residuals, and it gives you an approximate, a typical, an average prediction error for the residual. That then leads us into a new statistic called the coefficient of determination, r squared. R squared is the fraction of the variation in the values of y that is explained by the least squares regression of that y on x. Okay, that's probably a lot of gobbledygook to you right now, but I'm going to try and explain it to you a little bit clearer, a little bit more common sense as we go through this once you finish filling in the blanks on your paper. One thing to remember is it will remain the same. The r squared will remain the same no matter which variable is labeled x. Just like with the r, if you flip the x and the y, the r didn't change. If you flip the x and the y, the r squared is not going to change either. Okay, so back to our knee data. So we have knee and range of motions. Let's examine what r squared tells us. Suppose you were going to predict, you wanted to predict a future y, but you didn't know the x value. Okay, so the data was gathered some way or another, and we didn't know the ages of any of the people that had been measured. All we knew was their range of motions. If we were trying to make a prediction without the ages, then the best guess we could do would just be to take the overall mean of all the y's and say, well, the average range of motion is this, and therefore that's our best prediction. So for example, we have this set of data. Let's say we don't know what any of the x's are. Our y bar, our mean of all our y values, is 130.083. That's our best guess because we don't know the ages. Well, you can see that some of those points are very far away. So if I were to calculate all the residuals, the bars I just drew on the yellow graph, those are the residuals, the distance from the point to the line. If I were to calculate every one of those residuals and square them all and add them all up, that's what I get. So that is the sum of the squared residuals using the mean of y. So that number, if we didn't have the x's, that's the best we could do. Now, suppose we do know the x's. We do know the ages. Well, if we do know the ages, then our best guess is not the y hat, the y bar. Our best guess is the least squares regression line. We plug it into our calculator, we graph our scatter plot, and there's our least squares regression line. That's our best guess. So now let's calculate the residuals again. So once again, I draw lines from the points to all of the y to the line. I square them all and I add them all up. Alright, so this is the sum of the squared residuals using the least squares regression line. Do you remember what the previous one was? Alright, the previous one was over 1500. This one's 1085. So we've gotten better. Our error is less than it was before. And the question is, how much less is it? Well, by what percent did the sum of the squared error go down? So how much better did we go? We went from 1565 to 1085. So we went down by 480, around 480 out of 1565. That's 0.3062. So we went down almost 31%. That 0.3062, that's your r squared. So r squared is the amount of variation in the y values that's explained by the x values. That's where the r squared comes from. So now you're wondering, what should we say on a test or a quiz if you're being asked to interpret the r squared? So here's a typical test question. You have a scatter plot. It compares grade point averages and SAT scores. GPAs are the explanatory variable. You're being told that the r squared is 0.6502. Let's interpret it. What does that mean? Here's what I would want you to write. 65%, that's your r squared, of the variation in SAT scores, right, SAT scores is your y variable, is accounted for by the linear relationship with GPA. That's what I want you to write. Right? A generic form, blank percent of the variation in y is accounted for by the linear relationship with x. You should write that down. That's what you should say. Don't deviate from the script. Don't get cute, as it says there. Stick with the format. That's the interpretation that you want to say. All right, so put a nice big star next to that sentence so that you'll remember it. There's only three things you have to change: the blank percent, the y in context, and the x in context. Everything else stays the same. Okay, on to a new topic. We're almost finished. Outliers versus influential data. An outlier is an observation which lies outside the overall pattern. We've talked about these before. An observation is influential, so here's a new one, if removing it would significantly change the least squares regression line. You should always look for influential points in the x direction. So you should look across the x-axis and see if there's some point way outside the normal x value. If there is, it might be an influential point. So here's an example. We have a scatter plot and a least squares regression line of the brain weight for 96 species of mammals. I misspelled mammals. But you can see up here that we have all these dots. They're nicely clustered. We have a least squares regression line going across, and we have 4 outliers. We have an elephant, we have a dolphin, a human, and we have a hippo. What do these tell us? What do the outliers tell us? Well, looking at the dolphin and the human, they have a big brain. Their brain weight is big, but a body weight is small. So that tells us that dolphins and humans are smart. Big brain, little body. All right, so that's what that tells us. A hippo, on the other hand, a hippo has a great big body, a very small brain. So therefore, hippos aren't the brightest animals in the world. Elephants, they got a big brain and a big body. So hippos are dumb and elephants are just big. So look out, here comes a big elephant. So that's basically what an outliers will tell us.
That's all, folks.